Now let me define another extension of the definition of ring, and we call this structure as a sigma ring. We can also write it in this fashion, sigma ring. So this is an extension of the definition of ring in the sense that a ring was closed under the operation of taking finite unions and differences. If we change the finite unions to countably many unions, then it becomes the definition of a sigma ring. So a formal definition is a non-empty class of subsets of omega. So let me denote this class by say script S is said to be a sigma ring if it satisfies the following two properties, that given any two sets, their difference must be in the class, and secondly, if I consider any sequence then its union must belong to. So easily you can see that the second one is a generalization from the definition of a ring, because there we assumed only finite union. So naturally the consequence is that every sigma ring is a ring. Secondly, if I have a ring and it is closed under the formation of countable unions, then it is a ring, then it is a sigma ring. As you had seen in that in the definition of ring, we assumed only closeness under the formation of unions and the differences. However, we could show that it is closed under the formation of symmetric differences, the formation of intersections, etc. In a similar way, if I am considering a sigma ring, then it will be also closed under the formation of intersections. So let us write down that statement. If I have a sequence say En in S, then we can write intersection En, n is equal to 1 to infinity, as E minus union E minus En, n is equal to 1 to infinity, where E denotes the set, union n is equal to 1 to infinity. Now, if script S is a sigma ring, and if I am considering a sequence En there, then naturally the countable union of these sets belongs to the class S. Now E minus En also belongs, because this is the differences of the sets, and therefore if I again take the countable union, that is again belonging to the class S, and therefore E minus this is again in the S. So this belongs to S. Now since this is a alternative representation of the intersection En, this means that every sigma ring is closed under the formation of countable unions. In the previous class we introduced the concept of the limit of a sequence of sets. It was actually defined as limit superior of a sequence of sets, limit inferior of a sequence of sets, and if the two are equal then the limit exists. Now, we had alternative representation of the limit superior and limit inferior in the form of countable unions of countable intersections or countable intersections of countable unions. So, now if my initial structure is a sigma ring and it is closed under the formation of countable unions and countable intersections, therefore, it is also closed under the operations of limit superior and limit inferior, and therefore, if the limit exists, then under the operation of taking limits. So, we can mention that a sigma ring is closed under the formation of limit operations on the sequence of sets. One more extension of the definition of ring or algebra or sigma ring is the so called structure called sigma algebra or a sigma field. So, let us define it in the following fashion: sigma algebra or a sigma field. So, a non-empty class of subsets of omega. So, let me define this class as a script f is said to be a sigma field if it satisfies that for any given set its complementation will also be in the given class. Secondly, for any sequence of sets the countable union must also be in the class. So, you can see that it is a generalization of the definition of a field as well as it is a generalization of the definition of sigma ring. It is a generalization of the definition of field in the sense that in a field we had closed under the operation of taking complementations and unions, but unions were taken to be finite. Here we have taken countable unions. It is an extension from the definition of a sigma ring in the sense that countable unions are there and the differences have been replaced by complementations. So, in some sense it is one of the largest structures among the 4 structures that we have defined. So, we can write the comments that every sigma field is a sigma ring, every sigma field is a field, and therefore, every sigma field is also a ring. We can also say that a sigma ring closed under the formation of complements is a sigma field. A sigma ring containing omega is a sigma field. A field closed under countable unions is a sigma field. So, among the 4 structures, this sigma field or sigma ring is the most general structure. A related structure is that of a monotone class. A non-empty class of subsets of omega is called a monotone class if for every monotone sequence En in this class limit of En belongs. We prove that a monotone ring is a sigma ring and a sigma ring is a monotone class. See, we already said that in a sigma ring the limit operations are valid, and therefore in a sigma field also the limit operations are valid. So, monotone class is a particular structure which is something like in between a ring and a sigma ring, or between a field and a sigma field. However, it is useful in the sense that given a class, if I just look at whether the limits are there, then monotone class is confirmed, and in many operations that is what we finally need. So, let me prove the following theorem. A sigma ring is a monotone class a monotone ring is a sigma ring. To prove that a sigma ring is a monotone class, we notice that a sigma ring was closed under the operations of taking infinite unions and infinite intersections, and therefore the limit operations were valid. Therefore, a sigma ring is naturally a monotone class, because if a monotone sequence is taken, its union or intersection is the limit, depending upon whether you have a monotonically increasing sequence or a monotonically decreasing sequence. So, the first statement is valid as a sigma ring is closed under countable unions and intersections. To prove the second statement, let us see in the following fashion. Let R be a ring and also a monotone class. So, since it is already a ring, we have to only show that countable unions will belong to the given class to prove that it is a sigma ring. So, let us consider a sequence A in R. Now, if I take, say, Bn is equal to union of ai, I is equal to 1 to n, then it is a finite union of the sets in R, and therefore it will belong to R for every n. Now, the nature of this set Bn is that if I take Bn plus 1, then one more set will be coming. So, Bn is naturally a monotonically increasing sequence of sets, and limit of Bn will become equal to union ai, I is equal to 1 to infinity. Since R is a monotone class, limit of Bn will belong to R, as R is a monotone class. So, R is a sigma ring. This result is useful in the sense that if we want to create a sigma ring from a given class of sets, then taking all the unions etc. may be quite complicated, whereas if it is already a ring, if we ensure that the limits of the sequence of the sets is present in the given class, then it will become a sigma ring. So, it is something like a you can say a method of obtaining generated sigma rings from a given class which is already a ring. A somewhat simpler structure in this direction is a semi-ring. A non-empty class, say P of subsets of omega, is said to be a sigma ring, said to be a semi ring if it satisfies the following properties. That is, if a set is there then E intersection F belongs to P. That means it is closed under the formation of the taking intersections. However, another property which looks somewhat different than the ones which we have given till now is that if E and F are any two subsets of omega in P, and say one of them is a subset of the other one, then there is a finite class C naught, C1 up to Cn of sets in P such that E is equal to C naught subset of C1 subset of Cn, which is equal to F, and the successive differences of Ci's must be in P. I mentioned that it is a structure which is simpler compared to the structures that we defined just now, in the sense that I have not assumed the that union will be there or complementations will be there. You can see here through an example, if I consider say omega to be any set, and P is say the class consisting of the phi set and the set of consisting of singleton sets for all x belonging to omega, then this is a semi ring. Let us see how. If I take intersection of any two sets, then that will be empty set. If I take any two sets, since no set is a subset of another one, the second property is trivially satisfied. So, this is a semi ring. Now, why I said that it is a structure which is more simpler in nature compared to ring, sigma ring, field or sigma field, because now you see this set P, it is not satisfying properties of none of the previous structures. For example, unions of two sets are not there. So, it cannot be a ring, sigma ring, field or sigma field, whereas it is a semi ring. Let me take another example. Suppose I consider omega to be the set of real numbers, and I consider P to be the class of intervals of the form A to B, that means semi closed intervals. I am taking left closed and right open. Then this is a semi ring. To see the structure of this, suppose I am considering any two intervals of the form A to B. Now, if I take say A1, B1 and say A2, B2, then if I take the intersection of this, then if they are of this form, then the intersection of A1 B1 with A2 B2 is of the form A2 B1, which is again an interval of the same form. Suppose I take these to be disjoint, then the intersection will be phi, which is corresponding to the choice A is equal to B here. Similarly, I may take this on this side, say A2 B2. In that case, the intersection will be A1 B2, which is again an interval of the same form. So, in all the cases, the intersections will be existing in the class P. Now, suppose I consider two intervals such that one of them is contained into another one. So, let me take A1 B1 contained in the interval A2 to B2. Now, if I look at this, then I can consider n classes which are n sets. Here if you look at the second property of the definition of the semi-ring, then there is a finite class of sets in P, C0, C1, Cn, such that the smallest of this is same as E and the largest of this is same as F, such that their differences belong to P. So, if we look at this one, I can always construct sets like this. So, this set itself can be my C0, this can be some set, let me call it say C1 to D1, say C2 to D2, C3 to D3, and this is say Cn to Dn. Then each of them is a superset of the previous one. The largest is equal to the bigger interval A2 to B2, the smallest is equal to the interval A1 B1. All of the sets are of the same form, and therefore, they are satisfying the property that they are in P. If I consider the difference of any two successive sets, so for example, if I take C2 A2 D2 minus C1 D1, then it is equal to, now in this particular structure the difference is equal to C2 D2. So, I am removing C1 D1 from here, then it is becoming equal to C2 C1. So, if I look at the definition of the semi ring, then it is belonging to the class P. So, we have the following remarks. Phi belongs to P for every semi ring, because I can take two sets to be equal, and if I take their differences, then it will be there. An equivalent definition of semi ring would be a non-empty class P of subsets is a semi ring if empty set is there for any two sets, intersection must be there, and thirdly, if A and B belong to P, then I should be able to represent A minus B as the union of a finite unions of sets in P. So, this is an alternative representation of the definition of semi ring. A useful concept in this context is that of a generated class. what is a generated class? So, given a class of sets, if I consider the smallest ring containing C, the smallest sigma ring containing C, the smallest algebra containing C, or the smallest sigma algebra containing C, or the smallest monotone class containing C, then it is called a generated ring, a generated sigma ring, a generated algebra, or a generated sigma algebra. Now, to see this, suppose I look at say a set consisting of singleton set A, then phi A, suppose I say this is my C, then this is the generated ring of C. Suppose I take this same thing and I take phi A complement and omega, then this is a generated algebra from C. Since this is a finite class, therefore, this is also a generated sigma ring or a generated sigma algebra. To see that how this process becomes more complicated if I consider larger classes, is that suppose I consider say class say AB. Now, you can see in order to generate a ring out of this, I have to consider the empty set, the two sets, their union, their differences. As we have said, its intersection will also be there, its symmetric difference will also be there. So, now you can see that variety of sets B minus A must also be there, because we can take the difference of these two. So, a generated ring is of this nature, which is consisting of many sets. Now, you see how the process will become even more complicated if I try to generate a field out of this. If I consider a field generated from D, then the number of sets is much more. I will have to take phi A, B, then I have to take A complement, B complement, A union B, then A complement union B complement, then I have to take A complement intersection B complement, and so on so forth. So, the number of sets will be much more, and this shows that this kind of structures will be useful in the definition of probability, because when we want to introduce the probability of different events, then their simultaneous occurrence, their differences, their unions, etc., also will be needed in defining the probabilities. So, this type of definition will be extremely useful for our. Thank you.